Hi, good afternoon. I'm Dan Sweet, and I'm with Helicopter Association International. Welcome to our new monthly webinar series, and we have an exciting topic today. If you've been waiting in the waiting room for a short period, I do apologize. Apparently, Zoom changed their controls on me recently, and the buttons I used to push no longer work. So it looks like we've got a whole bunch of you joining in right now. I'm grateful that you were patient with us. As I mentioned, today's topic to me is fascinating. It's really an exciting possibility for us. Artificial intelligence in the cockpit. Now, if you're like me, you probably have already made a joke about co-pilots. I'm not a pilot, so I tread lightly there. Um, Artificial intelligence or autonomous flight, rather, is getting a great deal of attention in our industry right now. And we know eventually, and this is going to be a long ways down the road, autonomous flight will carry passengers, will be doing much of the work that pilots do now. That's, again, quite a ways down the road. Artificial intelligence hasn't seemed to me to receive as much consideration yet. And there are already many instances where two pilots are required for certain flight operations. And that's one area where I think that this could help. And then we know there's a pilot shortage too. And so by allowing artificial intelligence to support a pilot or eventually replace a pilot is a way or a method to help address that situation. Today, our panelist, we have somebody who absolutely knows what they're talking about. We're very grateful to have Dr. Luuk van Dijk. He is the CEO and founder of Daedalean, a Switzerland-based company developing flight control software for autonomous flight, with the eventual goal of creating an AI pilot that will measurably outperform human pilots in all their functions. Currently, Daedalean is working with regulators, leading aerospace manufacturers, major eVTOL companies to test and certify the first machine learning-based sensor systems for guidance, navigation, and flight control. He holds a PhD in physics and previously held senior software engineering positions at Google Zurich and SpaceX, where he worked on infrastructure, flight software, and machine learning projects, among others. If this is your first time with one of our webinars, we welcome you. We do encourage you to ask questions. This is pretty new information, so I expect there'll be quite a few questions out there. Please use the question and answer module within the Zoom system. I'm not sure, it could be on the side or on the bottom somewhere in your phone or however you're using to watch this. We know that there's a chat feature. Go ahead and chat amongst yourselves if you like, but we're going to pay more attention to the QA feature, and we'll get to all the questions following Dr. Van Dijk's presentation. This webinar is being recorded. We do encourage you to go back, watch what you might have missed, share the video with anybody else you think might be interested. It usually takes us about 24 hours to get these posted. We'll get them posted to both our our HAI website and our YouTube channel as quickly as possible. So let me stop sharing, and we will invite Dr. Van Dijk to join us. Luuk, please bring your camera up.
Oops. Okay. I guess it works now.
There we go.
Thank you for having me.
Yes, I appreciate it, loud and clear, and your camera looks great. Hey, I've got a question actually to kind of just get us started. We just announced the recipients of our annual Salute to Excellence Land and Live Award winners this week. And we recognize the work of two pilots who collaborated to address an in-flight emergency that could have had catastrophic results. Their efforts and decision-making ended up helping to prevent the tragedy. They got the aircraft on the ground. Everybody was fine. How might artificial intelligence eventually provide assistance to a single pilot in a similar situation?
Yeah, I saw that the story of these fine gentlemen, and I'm very glad you formulate the question in this way. How could AI help to do something? Rather, because often after an introduction like this, people say, "And now, how's your system going to save the day in these, dire circumstances?" And that leads often to an unfair comparison, because it's not that the general safety of general aviation today in the sky depends on people doing this type of heroic feat on a daily basis. But if you frame it in a realistic way, then, and I think it's very important to set realistic expectations on these AI systems, then we could definitely see how we could take. Imagine this in this event, we had a single pilot who had to deal with this extreme emergency of the power management going off the scale. It was the division of labor between the two pilots that contributed significantly, I think, to the outcome. So imagine this had been a single pilot. We could give such a single pilot doing perfectly legal and safe normal operations, finding himself or herself in such an extreme case, an electric co-pilot that, for example, could take over the guidance to the ground to find the safe spot, while the human pilot focuses on the power management. That could have been a realistic scenario in this case, and I think it's well within reach to build systems that could have such a backup plan ready. To give the single pilot, again, currently, perfectly legal in certain circumstances to have commercial single pilot operations. What if you give these people an extra pair of eyes that has their back, and we can start creating an aircraft that doesn't kill you if you let go of the controls, or it gives you time to worry about the extreme circumstances while the computer takes over, basic things like seeing where you are and where you want to go. This actually leads very much into the theme of my talk, which is we think that the path to full autonomy goes through giving existing single pilot operations a co-pilot, and then adding safety along the way at every step, rather than coming up with an unrealistic scenario where, just as this computer is going to fly and we won't need any pilots, which we think is not a good way to do this. So yeah, you've touched on the theme of my talk. Actually, we've done it now. We can stop here.
Okay, well, I'll tell you what, let me turn my camera off. I'll keep my
Yes.
microphone on for just a minute, make sure that your presentation comes up, and I'll let you lead in.
Okay, let me see if this thing worked as we rehearsed. You should be seeing something called AI in the cockpit.
Yes, I do see your screen.
Yes. And we have 64 participants, I guess it shows on my screen. So thank you for taking the patience to listen to me tonight. And thank you, Dan, Jasmine, for having me here tonight. So we are Daedalean. Everybody gets to pronounce it the way they want. I knew this when I chose the company name, that there was going to be differences of opinion. Everybody's opinion is equally valid. I say Daedalean. We are 7.5 years old. We are by now about 150 staff. We try to bridge the world between the academic world of machine learning, robotics, computer vision, and the other side, the pilots and aerospace industry personnel, people with experience designing and manufacturing aircraft. And our population makeup reflects that. So we started in 2016 with the idea, actually it was a very naive idea, that if you took the CPA skill test, it was a formal description of what it is you're supposed to do as the pilot during your exam, right? Which is supposed to be the bar. If you make that, you're allowed to fly. I know there's not a lot of other conditions you have to fulfill, but it's a blueprint of what the human pilot actually does. So we thought, if we make systems that do all these things that are enumerated here, and we measurably outperform the human pilot in every way, we should be good. We should be done. And we thought we'd be done by now because we were naive. And so we deconstructed this pilot and looked at what it is that he or she does. So it begs the question, what does the pilot actually do? And so a lot of discussions about autonomy and self-flying, also self-driving. People point out, my airliner already flies itself. The pilot just sit there and monitor things. And this helicopter, has an autopilot and a GPS. So what do I need the human for? So there's a misconception easily made by the lay people, but pilots know better. You're not there to move the stick. You're not there to move the controls and push the buttons. You are there to maintain a safe state. You do that by looking at the environment, seeing where you are, seeing where the aircraft is, seeing what state the aircraft is in, seeing what state elements of the environment are in, for which you need to understand what it is you're seeing. A cloud behaves different than another aircraft. Runway is different than a freeway. something taxiing on the runway behaves in certain ways. And so based on your semantic understanding of what you see or what you perceive, it goes beyond seeing, you can predict the next 10 seconds, the next 100 seconds, and you can try to predict where things would become dangerous and how to keep them safe. And based on that, you change the flight plan, which might, be at the level of you move controls a bit to move out of the way of to give the proper right of way, or you change your flight plan. And so the proper way to think about this was laid out by Professor Nancy Leveson of MIT in terms of hierarchy of control loops. So usually, and the control loop is, of course, a fundamental ingredient in engineering and thinking about how to build systems that do something intelligent in the world. So this earlier criticism that my aircraft is already automatic, it mistakes the level at which we're controlling the aircraft. So you can perfectly easily automate, and autopilots do this. And the cruise is often boring because the computer takes care of the normal case. But the pilot is on top of that control loop, monitoring if the lower level systems are doing a thing. So that means if we want to now build systems that take over the pilot's job to some extent, we can't just add another box in that bottom layer. We can't just add another instrument in the cockpit that says, beep, there's something wrong. Bob, you have to pay attention to me because there's something wrong. You have to make a new kind of instrument which fulfills new kinds of functions. Namely, it integrates all this data that it can find and helps the pilot maintain this safe state. So that's been maintain a safe state here. I'll say it again. So fortunately, flying is a lot simpler than driving. So the promises of AI helping you drive have been, through their typical valley of over hyped expectations and the peak of expectations and the trough of disappointment. Flying in itself, from a robotics perspective, is an easier problem. It can be summarized as don't fly into anything you can see unless you're 100% sure that you want to land on it. And you can make this a bit more precise. So if you take off, you want to not fly into masts and wires. You want to avoid other people that fly there according to the rules of the air. You want to be able to land, on purpose or emergency landing on a helipad or off a helipad. We have a similar graphic for a fixed wing, by the way. You want to avoid the mountain. You want to avoid the weather. And you want to execute your mission. The difference with self-driving and the AI applications there is that the safety bar is much higher because it's potentially much unsafer to sit at high altitude and high velocity. The stakes are higher and the safety bar is higher. So you're in a different corner of the design space. So our vision here is to not show up with, trust us, this box is 100% better than people. Dear FAA, let us fly it. Because even if it was actually true, they have good reasons to not believe you. And so what we want to do is we want to create an aircraft that is smart enough so that the crew can focus on these higher level tasks and can start interacting with the flight plan rather than directly with the aircraft, thereby freeing up a lot of mental capacity and making it possible to safely conduct single pilot operations, which are already legal today, with an extra layer of safety that is going to be hard to argue with. So this way, instead of having a mountain of obstacles to your autonomous flight applications, we are going to fly around the mountain by adding these safety features, and which of course brings upon the homework to actually demonstrate that, and then eventually come to a fully autonomous aircraft in the future after we have demonstrated that the interactions of the pilot are superfluous. So that's the strategy we want to roll out, and if we don't meet that bar, I think we should not be allowed to put such systems in operation. So we started simple and easy. Most people start to fly in VMC and VFR, learn to fly in VMC and VFR. Even if you fly IFR, you still are going to need a number of capabilities that are absolutely required in VFR. Namely, you have to see where you are, and you have to see where others are flying, and you have to see where you land. And seeing where you are is important because you know that you can't trust your GPS because it can be switched off by evil people that buy a cheap device on AliExpress. Traffic detection is actually, it's the law. Part 91.113 says that if conditions are visual, it doesn't matter if you fly IFR or VFR, each pilot shall remain vigilant and look out the window to give the proper right of way. And you all know, if you're a pilot, that you don't see everything out there, and that this system works because the sky is big and empty. Because there's a lot of things that you haven't seen. And of course, ADS-B is going to help there a lot, but there's also uncooperative traffic, and that's not a valid reason to fly into them. Then landing guidance is, people land aircraft, fixed wing and rotorcraft, with no machine assistance routinely. And for that, you need to find the place where you want to land and decide if it's clear or not. And we do this routinely without any ground infrastructure whatsoever. There's only, concrete or sometimes even a grass runway. So we decided to build systems that can do these three basic things. First, we call the system the VXS. It uses a downward fisheye camera to recognize the landscape and your motion through the landscape, and it provides a completely independent reading of position that you can compare to your GPS, and it's engineered in such a way that if they disagree, you should trust your eyes. So as long as we see something with texture, we can provide you guidance towards the ground, for example, for an emergency outer rotation on a helicopter. And we can see if the space is actually clear. Then visual traffic detection is our flagship product, which is the first one we're trying to get certified with the FAA. So we're in an STC project dealing with this. It's a system that uses a high resolution camera in the visual spectrum because if humans can do it in principle, there's a lot of information in the visual spectrum. And our system looks at all the pixels all the time and finds things that are very likely, likely enough to be aircraft that you should be alerted to it. And in the first version, we can show this on the screen along with the ADS-B traffic information and give you clues in which direction to look and what type of aircraft you might be dealing with. And we can also see flocks of birds and other, things in the air that are not cooperative. And the visual landing guidance, I already introduced it. It's a camera-based system that can find a runway, can find your position relative to the runway, can do the geometry, and can give you guidance to a fixed-wing landing. And there's an equivalent system for vertical landing. So why do we call these systems AI, you might ask? And when we started, AI was very much into computer vision and, recognizing that there's a cat in the video, recognizing faces in your Google Photos. The last, I would say, year and a half, everybody's talking about ChatGPT, which is an amazing piece of technology that I, at this point, have no idea how to safely apply in a cockpit. So when we say AI, actually, AI has been a marketing term since the 1950s. In the 1950s, AI was a computer playing chess. And that turned out to be actually easy. And when things become easy and we know how to do that, we no longer call them AI, we call them computer science. So 15, 20 years ago, it was almost impossible for a computer program to decide if a picture had a bird in it or a cat. Or slowly this became possible. And nowadays, you almost wouldn't call it AI anymore. So we call it machine learning. It's a class of systems that are engineered by having one computer program fiddle the knobs on a family of computer programs until it finds a particular computer program or a particular setting of these knobs that satisfies the quality constraints. And this is a different way than traditional writing of software. We use a thing called neural networks, which are also used in this ChatGPT thing, but I might have some comments on that. But so we're not doing the ChatGPT thing. We're not asking, oh, computer, tell me which way I should fly. We are having a little component that acts like a filter, a noisy filter on a noisy problem, here's an image, is there an aircraft in there? Or here's an image, where's the runway? And because we use this neural network, we had to invent some new things. So here, this slide is about why machine learning. And so what I tried to say earlier was, so the problem of drawing a box around this helicopter has been possible with computers only for the last, I would say, 10, 15 years. And to do it relatively reliably, is more recent. And then, but once you have this capability, you can do amazing things because human eye is a miracle in many ways. But you have to point it in a certain direction, otherwise you don't see things. It's better at seeing things that move, which can mislead you because the things are on a collision trajectory where don't actually appear to move. So we have a system that can, clearly outperform the human eye in almost every way, I would say, in this particular respect. And the only way to feasibly do this is with this technique called machine learning, which is often marketed as AI. And that means because we are professionals and we're not a bunch of amateurs that cobble together some demo, we want to certify this. We want to pass the FAA bar for proving fitness of purpose in absence of unintended function. And it depends on the kind of aircraft you fly, but it's part 23, 2500, and 1301 and 1309. Other things are like 1329. But in this case, we have to prove that this machine learning based component delivers the intended function, no more, no unintended functions, and no less, and that it is safe. The no unintended function goes into safety. The thing should not make things worse under any foreseeable operating conditions. And so that brings us to how do you do this? So for what we call classical systems, which are often contain computers with complex hardware and complex software, there are development processes. First, you have to follow the safety analysis and the system design processes defined in the ARPs. And then you have functions allocated to software, allocated to hardware, and the standards like DO254 and DO178 prescribe the amount of work you have to do in order for the FAA to believe that it's a valid thing, that it works as intended. And the interesting thing is, because software is actually very hard to prove to be correct, the only way that we can do this is by relying on the experience that if we do this amount of extra diligence, that's the design assurance level, we have a system that we think we can trust to some extent. And the interesting thing is that for a machine learned system, this extra pile of work that you have to do for classical software and classical hardware is not really possible. One of these things is called the traceability of requirements, meaning we're not just writing software, we're writing very detailed requirements and we're mapping the software to these requirements. So these neural networks, basically their description is a million numbers. And what people in 2016, when we started, were very worried about is that you can't trace requirements from the value of these numbers to these requirements. So that means we have to come up with a new way of doing this. And when we started, that meant we realized that, first of all, everybody at the time believed neural networks, machine learning, AI was fundamentally uncertifiable. And AI, in the sense of computer systems that we don't really know how to do yet, they are fundamentally uncertifiable because we don't actually know what they do yet. With machine learning, we actually know what they do. So we thought the reason people believe this is wrong. And so it should be possible to prove fitness for purpose in the absence of undetected, unintended function. Sorry, it's late here. But that means that we not only have to build a thing, which is normal in engineering, we do not only have to build the evidence that the thing works as advertised, which is normal in aerospace. In this case, we also have to develop the theory of how to even argue that for a machine learning component. So we spent a considerable part of our 7.5 years doing that. We did 2 projects with the EASA on concepts for design assurance for neural networks. And then we did 1 further project with the FAA. All of these 3 resulted in reports where we lay out a framework and approach, methods towards this. We're trying out this approach in our first STC project with the computer vision machine learning based traffic detection. And that's where we are today. So with that, oh, that's where we are today. That was this slide. So this first instrument is going to be certified as pilot assistant. So it's not that we take the cameras, feed them to a giant neural network that we train on whatever, and then directly connect it to the controls of the aircraft. What we do is we put the machine learned function in the box where we really need it, where we have no alternative, and it fulfills the requirements there, and we have a means to prove that. And then the function of the system as a whole, in this first instance, is help the pilot find the traffic. The next function is going to be help the pilot find the landing site. For the landing site finder in a helicopter, we can have an emergency landing plan ready before the event happens, so that when the auto rotation takes place, if you take your hands off the stick, the thing will auto rotate to a sane and your least bad option. And so, and I think we can outperform the judgment of the typical human pilot there. So we're in the middle of that STC project. We hope to close the remaining SOIs in the course of this year, which is an ambitious timeline, and then have passed the hurdle for the first one and can quickly pass the other ones. So with that, the STC in question is with partner Avidyne. We're bringing this instrument to market, 3 cameras and a box that does the processing. It displays the traffic mixed in with the ADS-B display, and it integrates naturally with the existing cockpit instruments. We have other things in more experimental stages where we actually interface with the autopilot, the 4-axis autopilot of the helicopter, and can come towards the system that can reduce the workload of the pilot by being a second pilot. So with that, I hope I have met your expectations, and I would like to open the floor to questions.
And I'm bringing my camera back up. There we go. That was fascinating. I really appreciate the presentation, Luuk. We'll start out with a question from Eric, and he says, "Thank you for the presentation. As new entrants come into the airspace, can you expand, 1, on the training data set, and 2, speak to how this impacts the certification of the system?"
I don't understand the first part. As new entrants into the.
Well, maybe let's just leave that out. Can you expand on the training data systems, this
Yes.
training data set, and then
again,
how it
right.
impacts
And,
the?
Right. That's actually a very good question. So if you come in with the expectation, oh, people talk about AI in the cockpit, I have this abstract entity that behaves just like a pilot. Pilots are trained. We need to train this thing to behave in all kinds of circumstances. We don't. What our machine learns, our AI component does is it's restricted to here's an image, draw a box around the aircraft. That's a hard enough problem. Once you have that, you can build all kinds of classical systems to do these things. But yes, to build this machine learning system, it needs to be trained. And the training itself is a metaphor. It's a valid word to call it. It's not like a pilot that has to be making a certain number of hours, although in a certain sense it is. We have to have lots of labeled examples of this is what this little thing is an aircraft, this little thing is not an aircraft. And gathering that data is actually expensive, and you have to have it annotated in some way. So we have an office of human annotators that have to so we gather data from flying around in representative environments. We gather lots of footage of things with aircraft and things that are not aircraft. We need to have this ground truth labeled by our data annotation team, and then it goes into the neural network training and verification pipeline. And the essence of our verification strategy is to show that training set is representative of reality. Because if it is representative of reality, then and your machine learning algorithm and your neural network fulfill certain mathematical conditions, you have valid mathematical reason to believe it will work in the wild the same as you tested in the lab. And so this is the crux of our verification strategy. the managing the data and making sure that the performance of your network, it's called, generalizes to the real world. And with this, we actually have a very strong fundament under this certification strategy. I hope I answered the question there.
I'm guessing so. We're getting a bunch of questions in now. Let's go with one from Abraham. Would the system display low altitude obstacles and other air obstacles such as balloons, birds, or UAVs?
Yes, yes. We carefully constructed the system to also show you that there is something, even if it's not sure what it is. So the thing that says there's something there and the thing that tries to guess what it is, they are relatively independent. And because it would be very tragic if we didn't tell you not to fly into an air balloon that looks like a massive commercial, for a bottle of wine. So you have this massive bottle of wine flying through the sky because somebody thought it would be a great campaign. We fly into it because, who expects a bottle of wine? Actually, in driving, I saw a similar example. There was a guy in a chicken costume, running across the road. So, anything that starts with "this is what a human looks like," and we're going to is fundamentally badly designed. So we recognize flocks of birds and things that we don't recognize. We'll still tell you, I think it's suspended in the air. Don't fly into it. The ground is actually a very interesting source of false positives. So it turns out that a major trick of the trade here is to tune your recognizing function such that it doesn't throw away too many things too early on, but that you use some signals to throw things away later. And there be dragons. For example, it makes a great demo if you can see things that move, right? And as a human, you pick up things that move. If you design your system so that you use the apparent motion as a cue, as a signal to find things, you have made something that is probably useless when you're on a collision trajectory. So in the dangerous case, when you're on a collision trajectory, things appear to stay in the same spot, they just slowly grow. So what we want is a system where everything that we see counts as evidence that we would have also seen it if it was on a collision trajectory. So that makes it, it puts the bar harder, but it means that all the things we do see count as evidence that we would see them in dangerous cases. I think I'm now, off on a tangent that wasn't really asked, but I can talk about this for a long time.
Well, let me ask about, this is just a personal question that came up for me, question for items that aren't necessarily as visible as objects in flight. And what I'm thinking about are maybe like power line wires. Things that are,
very good question.
There, yes. But they're almost invisible sometimes.
Right. So it's a separate system. It's a separate use case, separate data. It's very interesting. So as a human, you use lots of cues, and our system can do that too. So if you see this mast, or if you see the string of masts, even if you don't see the wires between them, there's a wire between them. If there's suddenly an orange ball suspended in the sky, you can infer that this slight discoloration that you wouldn't have paid attention to, probably a wire. And so we can give the system this context and have it picked up. And there's another interesting thing, which actually, if you think about it, you would already know. You can see things that are smaller than the pixel of a camera. So you think, oh, if it's smaller than a pixel, you can't see it. No, the probability that it reflects a photon is still there if it's way smaller than a camera. So you can actually see these wires, but they take the form of these subtle discolorations that hang in the distance. And we can totally outperform the human there. We can find cables that you had not thought about. And for helicopter operations, it's particularly useful because we know many examples where, I wouldn't say the dominance, but, a leading cause of incident is flying into a cable that you actually totally forgot about was there. And so that's, we can give you an extra pair of eyes that has your back, but also your front. And so in this way, but then you can make a very primitive instrument that then shows this to the pilot. But then to communicate to the pilot, you'd have an extra screen. Your eyes would be there instead of outside where they would be. So we think that this kind of knowledge is better brought into a system that says, keeps the whole thing in view. And it's only if it knows that the pilot is currently on a trajectory where he has a chance of hitting it, says, I wouldn't do that. Or, gently pushes back on the stick with an audio signal, or actually says, hey, Bob, don't go there. There's a wire that you haven't seen. And that whole field of HMI we're scratching the surface of that, and we're exploring that. And we think it's very important to just not just add to the noise, but actually, add to the safety.
Okay, well, let's jump to a question from Marana, I guess. I hope I pronounced the name correctly. Could your system, for example, monitor if the aircraft is getting icing, or also monitor health parameters of the aircraft's internal systems?
Right. So the current central suite we're looking at is cameras that look outside. And so we figured that, detecting that you have icing is a solved problem, and, making a reliable sensor for that does not really require AI. It just means, it requires a budget and a good sensor. Having all these sensors integrated, or, and if you don't have inferring that your icing sensor might not be working because of this other combination of things that happen to be going on, and going, hey, I think this icing sensor is off, or finding, so you have different sensor modes patching together all degrees of freedom in your environment. And then suddenly this hole appears, having the system figure out, this sensor is dead. Or I think I no longer hear my tail rotor. I wonder what's going on. These things are definitely within reach of technology today. And then the challenge is to prove that you're adding safety and not adding more complexity, for which you need higher qualified crew to deal with the inevitable more complex failure modes. So it's a very intellectually, so this is what the joy I get out of this. It's intellectually very satisfying to think of ways that you make systems that are, clearly better in every way, and don't introduce these traps that you've actually made something that, so I find this thinking about safety very inspiring.
Let's continue on with another technical question. Can you combine optical camera data with infrared data as
Yes.
visibility degrades?
Yeah.
And
Yep.
For me to add a question onto that, could you also include mapping data sets from, say, Google or
Yes.
whether? So
Absolutely. So the goal is to integrate all the information that we have in such a way that if there's something wrong, it's not up to the pilot to decide it's wrong. So our visual algorithms for positioning work out of the box in the infrared. And it's a simple way to outperform the human by cheating. You add a wavelength that isn't there, and then you can fly into, if it's a long wave infrared camera, you can go pretty far into IMC conditions. Not all the way. At some point, if you don't see, you don't see, and that's dangerous. But it is an advantage that how do I put this? You can cobble more variations together with these systems than you can experiment with the composition of the human body and mind. And so this is one of the reasons why I think if you take slow, realistic steps, eventually every generation of the instrument builds on the knowledge of the whole population of engineers and safety people and related people that are working on this. So it gets better. And humans evolve on the scale of the evolution. So humans, even if they are amazing in many ways, but it's inevitable that they end up as the weakest link, right? If you think about it. And I think overselling it and saying that is the case now would be doing disservice to the industry. But it is inevitable that we were not built to control things that fly at 150 knots, at 6,000 feet or lower is actually harder. And so that you can build on machines, and that these machines get better and better, and then the crew can retreat to a position of monitoring that everything's safe on timescales that humans are comfortable with. I think is an inevitable trend of engineering.
Amanda has an interesting question. We've talked about the sensors a little bit already, or quite a bit already. And we've talked about the weather degradation, where it might be a gradual effect. She's asking something about that is much more sudden. Brownouts. How would it handle a situation like a brownout where all of a sudden you're landing and then you have zero visibility?
Right. Then our cameras are with the technical term SOL, but because we can't see because in the visual. So what we can help with maybe is not get there. Maybe we can recognize possible brownouts on approach before it's too late. So it just adding a bunch of cameras and some magic AI source is not going to make it's not going to change the laws of physics. And brownouts typically, your long wave infrared is not going to help you either. What we can recognize is that this looks like a patch of snow where I'm going to have a massive whiteout. How about I don't go land there? And or there's a twirling tarp, that would be a tail rotor hazard. These are things we can help with. We cannot make it. We can't switch off gravity and danger with just a pair of cameras.
Richard asks, well, actually, let's start with a question from Neil. What developments in sensor technologies do you anticipate in the next decade?
I expect that the LiDARs will keep getting cheaper. That's driven by the automotive industry. And then it will be possible to have solid state LiDARs with good resolution and good range that are usable for our use case. So your typical automotive LiDAR has too short a range, or you have to pump up the power, which is not nice for other people flying around. So I think LiDARs will become cheaper, and that's another way where you can add extra sensors, extra redundancy, a certain amount of IMC tolerance. We use visual spectrum cameras. We're pretty happy with how they are. It's the resolutions that are there are high enough. We're more bound by the lenses, and we're bound by computing capacity. And ironically, the hardest thing in the past 7 years is getting compute equipment that's powerful enough and certifiable to do the kind of powerlifting that we need on our. So it's not so much the sensors, it's the compute power. And it's there. In a data center, you have unlimited power. But putting it in a box, your typical helicopter builder would like this thing to weigh absolutely nothing and consume no power whatsoever. So if we show up with our 4 kilogram box and 150 watts for the first generation, they were like, yeah. Don't worry, it's the first generation experimental thing. But you can do that thing in an airliner, but not in a helicopter. So that's actually I expect that we will make some progress there. And then there's an interesting constraint in the aerospace, in the avionics world, that the volumes are so small that for most manufacturers it's not an interesting field, and they're not exactly dying to give us the level of documentation to get our system certified. So we're fighting this battle with one hand tied behind our back, and we end up having to take on more and more of the system design ourselves, because otherwise we can't get the certification documentation together. That was a surprise compared to 7.5 years ago.
Well, that actually brings up a question from Jim, and you just answered, I believe, a good portion of it. Are there any other hurdles that AI is facing for certification in aviation?
Well, so I think we've made super good progress with the ARs and the FAA. We found, contrary to what everybody said, the FAA will never do this and they will always do that. We found a very willing ear. If you come with, if you show that you've done your homework and that you take their concerns seriously and you try to learn to speak their language, because that was actually, I alluded to that in my introductory talk. I tried to bridge these two cultures. People that make apps for phones should not be allowed, within typing distance from a keyboard when it comes to programming safety critical software. But people that come from academia and robotics have no idea what the concerns are, for safety. At the same time, words like random, mean something very specific for mathematicians, means something completely different for aerospace safety engineers. And so to learn to speak these languages and address these concerns is it's humans talking to humans, building a story for humans that this thing is safe. That's grounded in firm reality. I completely lost my train of thought. What was the question again?
Well, I think
we found a very willing ear with the regulators to certify the AI when we came up with a plan. The hurdle has been this compute equipment, where to use these fantastic GPU chips that people have, they're just not going to give me the documentation because they're going to sell 10,000 units at best, and they would kill any product line that sells less than 100 million. And then the reputation risk of being involved in an airplane or a helicopter crash, is probably not worth it for most big ticket. So getting the sort of we did not anticipate that we'd had to design our own PCBs and write our own FPGA codes.
Okay, well, when you talk about the certification and the human factor, let's slide over to the human interaction side of this.
Yeah.
We have a question from Alden. It's a little bit long, it's a little bit complex, but
Okay.
Alden is asking, Reliable Robotics, Robert Rose recently made the following statement on a podcast, quote, "I'm not comfortable with a system where people say, well, because it worked for several thousand hours, because we did so many lanes, it's safe. That's just bogus. That's not the way these certification processes work."
Right.
Training a neural net with lots of data and then testing it against lots of data, which seems to be what Mr. Rose is talking about. How do you feel about that statement as it relates to your planned certification map?
Right. So that's a very good point. I know Mr. Rose well because he was actually my boss at SpaceX, and so we've talked about this a lot. So actually, for DAL-D, bringing us 10,000 hours of service history is a valid argument, but DAL-D is suitable for minor things where you don't care if you switch it off. Our neural network training and verification is not like that. We don't build the whole thing, then fly it for 10,000 hours and say, look, we saw this many aircraft, therefore it's good. The argument has to be much stronger. You have to actually show with considerable amount of evidence that you would see. So a typical requirement for such a system as the traffic detection looks like with probability 95%, we establish a track within 2 seconds of the aircraft entering the detection range. And for those that we don't, within 4 seconds, this many percentage. And that percentage is 95% is in itself not, that shouldn't let you write it off. For radars, you have a finite probability of detecting something. So, and these, you can make a radar to DAL-A, and the radar still has a chance of not seeing things. So how do you argue to a DAL-A level of so 10 to the minus 7 or 9 that your visual traffic detection system is good enough? It's not by just flying it around for 10,000 hours. You have to carefully architect your system so that you can build this argument. I was alluding to something similar earlier. You can make a cool demo if you use the motion, but then you can't use the fact that you saw it when it moved as evidence that you would see it if it didn't move. So here, in this case, the neural network itself has two important numbers, the precision and the recall on a data set. So given one image with an aircraft in it, how often do I miss that aircraft? That's a false negative. And how often, if there's no aircraft, do I say that there's one? So in these numbers, if you make a very good network and you have a very good training set, you can make a big enough set to say that this probability is 83% precise and 86% recall, and these numbers are within these bounds. And then you have this one component. Then to glue that argument to your system, you have to design your system in such a way that these probabilities multiply and add up in the right way. So you have to design your system so that this works. And in the case, I can give you a taste of how this works. If you look out the window, you blink and you don't look again, and then you try to memorize, did I see an aircraft, and use that to avoid what you saw. Other example, if you look out the window, see the runway, then close your eyes and fly to what you think you saw, you would not have a very high chance of successfully landing your aircraft. When you approach, you have every frame that the camera takes, you have a new chance of getting it right and getting it wrong. And from one frame to the next, these error probabilities are correlated, but after a while, it's a new, fresh roll of the dice. And if you roll the dice, often enough, then statistics and the central limit theorem are with you in if you design your system correctly, that the probability of getting it always wrong consistently drops off far enough, and then you can put something on top of that that says, and the probability that I don't notice that I'm not actually seeing the runway, goes to epsilon. So you don't do this by, flying 10,000 hours. You do this by very carefully. So we have a motto in the company that says it helps if you know what you're doing. So this is an example of, to build up this knowledge and build up a team that can come up with such arguments. It's actually a fairly alien form of thinking to most aspects of aerospace engineering. So this is data science. This is the kind of math that you find, in certain pockets in university, not directly associated with making avionics. And so when I created the company, I thought exactly, there's value in bringing together people that can build up such arguments to build this type of certification evidence. So to summarize, your criticism is 100% correct, and that's why we don't do that.
Okay, I know
I hope I answered the question.
Yeah, I know it's very late where you are. Getting towards the top of the hour. We're not going to be able to get to all the questions. Let me finish by asking, to take that a little bit further. Certification seems like it's going to be not an issue. I'm part of a generation that grew up with movies that showed flying cars, the goods and bads of artificial intelligence. How do you achieve human acceptance of a passenger flight powered by artificial intelligence?
Right.
What's your process there?
So I don't have the complete answer ready, but I have an analogy that has been used by others that 100 years ago, if you went into an elevator, there was a guy in a little costume who would push the buttons for you. And elevators at that time were dangerous, and then regulations were introduced, and elevators became a lot safer, and it became acceptable to push these buttons yourself. And nowadays, if you go to an elevator and there's someone there to push the buttons for you, you're like, what's wrong with this elevator? If you look at in one of my presentation decks, I have a photo of the cockpit of an early Boeing in the 1950s. There's a lot of people in there. There's navigators, a radio operator, there's a mechanic. And nowadays, if you walk into a cockpit and you see that many people, you'd go like, what's wrong with this aircraft? Why does it need so many people on board? And so I think that this is one of our strategies by rolling it out through the OPV. We give safety edition first. We're going to move to there's an intermediate phase where the crew interacts with the flight plan. Then we introduce command and control link to the ground. You interact with the flight plan, from the ground crew, because there's nothing on board that you could do. Take a rocket, where Mr. Rose and I worked on. If something's wrong with that rocket, not a lot you can do from the ground. The computer basically has to handle it for you. And so we come through this phase where the interactions are at the strategic level in the flight plan, not so much at the tactical level. And that means that when the command and control link drops, we're not in a state of panic, but the computer is going to look at its watch and say, okay, I haven't heard from the ground for 30 seconds. If I don't hear from the ground for another 30 seconds, I'm going to find a land as soon as practical site. Or, given the risk of my mission, I'm going to land as soon as possible, to name two extremes. And we can, and so once we have this phase, I think people will see. You have to also remember that for every heroic case where two people saved the day, there were people that flew into IMC or didn't see this cable or didn't save the day. And so if you gather the evidence, and that's where I think the 10,000 hours does become a valid argument for the public acceptance. If it becomes exceedingly rare that something happens with something that currently has a lot of, shall we say, headroom for safety, such as commercial helicopter operations, then this acceptance will come.
Dr. Van Dijk, thank you so much for your time this afternoon. I think we could have easily gone for several hours on this topic. I suspect
I'd like to
even try to have you back again in the future for updates. But no, this was fascinating, and I really enjoyed the presentation today.
Thank you. I'll be happy to make it available, and thank you for having me, and I welcome further questions.
Okay, well, I'm going to go ahead and wrap things up today, and just finish with a few housekeeping items. As we always finish up with our webinars, we do appreciate, whoops, get to the right slide there. There we go. We are now on the second Thursday of every month for our webinars. We have an update with Boeing. Actually, looks like I got the title in the wrong spot. Boeing update, we'll be discussing improving operational efficiencies throughout the helicopter life cycle. That will be the February 11th topic. The March 7th topic, which I accidentally replaced with the Boeing topic, is going to be a state of the industry address with Jim Viola. That will actually be a live event. There's going to be some special news that'll be coming up at the HAI Heli Expo. There is a question mark there about the date of March 7th. The problem with that is that's the week after Heli Expo. We're making sure that everybody's going to be available to attend the presentation that week. But it's going to be something that a lot, especially the HAI members, are going to want to attend, and the industry, I believe, as a whole will find interesting. We're also looking at accident investigation webinar and preventing auto rotation mishaps. And the one I didn't have on there is hydrogen-powered aircraft. So we're trying to get into some of the new technology coming up. We at HAI love to communicate. We love to share news. We have a couple different publications that are a couple different products that will help you. Rotor Magazine is an award-winning quarterly publication. This is our 75th anniversary edition. It's going to be going to press. We thought it was going to be already at press. We delayed it because there's some things that we just didn't get quite right. We want to make sure it's perfect for the 75th anniversary. It's going to be spectacular. It's going to be a much thicker edition than normal, and it's going to be something you're going to want to look through from time to time. Rotor Daily is a business daily news aggregate source. We do the Google searches. We do the searches through EASA, the FAA, to find the news that's relevant to you, to our industry, so that you don't have to. We are happy to send that to your email box every business day. Easiest way to subscribe to both of those is go to rotor.org/subscribe. There's no cost for the magazine or Rotor Daily unless you live outside the United States, and then there might be a small stipend for shipping the magazine. That would be the only thing. We may be sending a questionnaire to you shortly. If you do receive one, we ask that you take just a few minutes to let us know what you thought of today's webinar. If you want to see Dr. Van Dijk back, please let us know that as well. HAI is a membership organization. It's very important that we're providing the services that our industry needs and wants. If you have some ideas, concepts of what we could do or we should stop doing, please let us know that as well. The best way to do that is through an email to our president and CEO, James Viola, president at rotor.org. He sees them all. He passes them out. He responds to all of them. And we will get your answer for you. That does conclude our webinar for today. We appreciate that you took the time out of your schedule to watch, and we hope that you'll join us again very, very soon. Until then, we hope that you be safe and fly safe.